Okay, thank you everyone. Welcome. So we're going to get started now. A very quick introduction. Welcome to Xiaoli Wu. I think many of you have met Xiaoli while she's been here visiting us for the past 4, 5, 6 months now. Yes, and we're going to hear a talk about her research. So very much looking forward to this, about information displays and visual cognition. So thank you. Over to you.
Thank you, Professor Duncan. Good afternoon, everyone. I'm Xiaoli Wu. I come from Nanjing University of Science and Technology in China. I'm delighted to be here and share my research. I'm an academic visiting research scholar in UCLIC. My corporate supervisor is Professor Duncan. Thank you, UCLIC invited me to have a talk about the correlation within information displays and visual cognition. I will introduce myself. I'm a professor in Department of Industrial Design at Nanjing University of Science and Technology. My major is human-computer interaction. I have got a PhD degree of mechanical engineering from Southeast University. Southeast University is in Nanjing, Jiangsu province. And I have a 1-year experience research in Australian National University, and now I'm visiting UCL. I'm leading the lab of human factors and information system interaction of design. Our lab is a member of Ministry of Industry and Information Technology in China. And our research area is about visual cognition performance, the physiological evaluation mechanism. We also discussed the aero cognition and the correlation with design factors, and also about information integrated and visualization method. Our study applied some fields. There are 20 persons more than 20 persons in our research group, including the researchers, PhD student, and graduate student. In 2017, I have been to Australian National University and have been the member of research group in human-centered computing. My cooperated professor is Professor Duncan, Tom Digging, I'm sorry. And we have finished my research project about congruent effect on factors of information search and visual cognition. And I want to share about my research area. The first is about physiological evaluation mechanism. We have established the 4-step to evaluate the user interface and information displays. We have established the experimental paradigm about eye tracking indexers and ERP indexers, EEG, and also about EMG and other linked behavior response. And we also discussed about the correlation with aero cognition and design factors in complex testing interface. We have established some models about aero factors, visual cognition. We have established the mistake perception, attention failing, perceptual confusion, memory lapse, and neglect model. Based on the physiological experiment, we can analyze the user's cognitive error recognition. And we have got the correlation evaluation about error factors, visual cognition, and design factors. We also discussed the virtual information and eye control interaction based on the cognitive performance. Several of the eye technologies about human-machine coordination, eye control interaction, cognitive performance, multi-channel cooperated cognition, and cell. We have applied about areas is about interaction design of aircraft co-locate, information displays of pilot cooperative test. And also we have explored the presentation mechanism of information visualization. It's about we need analysis human cyber physical system and the data of intelligent manufacturing, water simulation of factory environment. So we have established the industrial integration platform of solar manufacturing. This is about our Xiaoli project. It's supported by National Nature Science Foundation of China and also supported by Jiangsu province. We also have finished some project. It's about evaluation massing, error cognition mechanism, and also about the design strategy. So we have finished some. So today, I want to share a study, a little study about how information within the perceptual span guides visual search and its perception. So first, I want to introduce the several conception. We can think of visual region. What is a visual region? Our image is can be divided into 3 regions. It is within 2 degrees. It's full field vision, and the 2 to 10 degree, within the 2 to 10 degree is a peripheral field vision. So it's a very useful field of vision, and the others region is a peripheral region. So the vision resolving and the cognitive processing abilities are very strongly listed. So we also need to know perceptual span. The first introduced the conception of perceptual span by McCoy and Rohner in 1975. They argued the spectral extent processed by peripheral describing the size of the visual field in which information is acquired during reading fixation. So, in 1916, the Martin also find the information 1, 2, and where is the boundary diagram. So we need to know the fixations. It is a fixation. It's only within 250 to 300 milliseconds, but it's a three process taking place. So the first equal the visual stimulus, it spanned 150 milliseconds, and then simple peripheral vision. So can plan next second. So we want to know, is this the field within the full field region or peripheral field region? Maybe it's a peripheral region. And when the next second is within the peripheral field region or peripheral region, so it could define it's within the peripheral field region. It's a perceptual region, but maybe it's a second is outside the peripheral region. So we have investigated set many reference about perceptual span and eye movements. We can find where and most the eyes during reading is strongly modulated by ongoing cognitive processes. So there is a sharp decrease in visual acuity from cancer to peripheral vision. So information is extracted primarily from the center of the visual field of at 2 degrees during reading, but also from up to 5 degrees of the visual field. So there are also many theories support of peripheral region. We can find the easier, the more useful peripheral region is, the easier it is to distinguish when the tangent is on the peripheral. And the less necessary it is to use the type of the circuit required for the test. So in summary, this study suggested the presence of test relevant objects, facilitates guided visual search and processing of information. So we want to know, is this I want to know how does information within the perceptual span efficiently guides information search. So we propose that information within the perceptual span can guide visual search and aid perception. So we have studied this. We have done this study to explore the guiding effect of test-related information appearing in the perceptual span on visual search. It is an information interface, and we can join. It's a foveal region, 5 millimeters distance from eyes in interface. So we can join the foveal region, and then it is, it cannot find. It is a foveal region. So, I'm sorry. So it also we think it's within the perceptual span. And then we have 3 hypotheses about is there any significant effect on the location of test-related information presentation on reaction time, gaze duration, and counts. And also we want to find additional swift circuit and bring the gaze into the area of interest within the perceptual span. And the third is range of perceptual spans with attention. So we have enrolled 48 participants, and they were divided into the 4 groups. AB is the left or right in range. CD is left out of the range. And also we want to set the independent variables. It's a 4 group. So the experimental color is gray because the color is influence recording eye tracking. So with the gray area marked as a perceptual span range and the center high luminous area as a visual range of the eye gaze area. So we can find the participants were required to search for the tangent, and we can record the reaction time and the eye tracking. So we can find there was a significant effect of range orientation on reaction time, and the reaction time of the guide information appeared within the, sorry, let's see here's, within the perceptual span range was less out of range. You can see the reaction time of the right orientation was less than on the left. So we can join the, we can analyze this data of gaze duration and gaze count. There also is a significant about range and orientation based on the gaze duration and gaze count. So we can analyze this, the range and the orientation conditions in which the guided information appeared had an effect on visual search under the test. The gaze duration and the count were less than out of range. You can see when the guided information appeared, the perceptual span, the reaction time was less right orientation than left. So we can join the circuit tracking. When the guided information appeared outside, it's outside the perceptual span. So there were more gaze. You can see the more gaze count. The eyes needed to spend more time searching for the tangent. And there were more ineffective searches. On the contrary, information appeared within the range or provide more consistent and systematic guided information effect during the research, and participants tend to be directed to the tangent area, less gas count. So it can be indicated information appeared within the perceptual span can guide participants to reduce invalid search. So we need to discuss the gaze circuit moving. When participants move their eye in order to place a central foveal on the stimulus, they want to see clearly. So the same constraint appear to visual search when participants can rapidly process more information around this gaze point in this test. So we can, based on the Scotter's certain model structure, it is structure introduced the model, we can join the information, the moment of information recognition completion depends on the gaze circuit plan, move from information n to n+1, whereas subsequent circuit plan is initiated when the first second plan is executed, which is more likely to happen when information n is easily to recognize. So we can establish the model of eye movement of visual search. We can see the first information is here, and it can analyze this. This is the reception span, and it's the first gaze point is fixation. So when is a tangent, another fixation. So participants need to plan the circuit and to find the tangent. So it another the second information. If it's unable to scan, can cancel, could find the information. But if cancelled, it's find another, maybe here or maybe here. So it's need spend more time to find another information. So we need to do the experiment 2. We want to know during actual searching AOI that I reach in connotation and interconnected tend to attract multiple repeated gaze behavior from the observer. So we can propose the following hypothesis. The information related to the test appears in the perceptual span, which has a certain guiding effect on the tangent search. So we need to discuss the adjusted interface. And over there, the information could find its adjusted the right region. So the independent variable was navigation interface right side, traffic sidebar information display. We also recalled the trial participant in group B is right in range to continue the experiment named group E. So we can compare, we can got the data about reaction time and eye movement index. So we can find is a significant on reaction time, gaze duration, and gaze count, circuit time. So there was significant effect of participant reaction time, eye movement index during visual search. So the adjusted, this is adjusted, is group E. We can find it's more consistent with visual percent pattern. So we can join the gaze circuit path and compare the group B and the group E. The participant should get the more gaze point in center area, and the less. The second path also shows that there were repeated there was a repeated left, right, and up, down, bad, and false varying of the information content. So we can join the gaze second and gaze the path. So the first we want to join the group B. It's capital participate. So the first we can find is information 1. The yellow is guided information, so it is find the tangent. So it's information 2, and it can find because it's within the perceptual span. And this it's the second within the perceptual span, and it's find the third information, but it's need to find where is the third information. So it's more past of gaze point, but it's not within the perceptual span. So it's here. So it's so long pass, and it will, maybe it will, or there is not find this information 3. So we can compare the group E. It's adjusted information. We can find it's maybe it's the same 1 and 2, and the third information is within the perceptual span. So it can find the information 3, it's within the perceptual span, and then to find the information 4, so it can swift spans of attentional point. So we need to discuss the experiment 1 and 2. The analysis of environment data shows that attention shift to induce circuits brings gaze into the area of interest, and perceptual span swift with attention. So we also can find the adjusted information display was more consistent with visual perceptual present pattern. So it's conclude attention swift caused circuit and brought gaze into AOI, and that perceptual span moved with attention shift. So we can explore the method of perceptual span guide information search. The first thing we need to analyze is the information. Maybe it's in perceptual span, or it's swift within the perceptual span, and then we can join the circuit path based on the eye tracking experiment, and then we need to adjust the position of information, and we can analyze the different group, and we can adjust the interface display. So we can get the redesign. We can redesign the information, mapping information search, perceptual path. So we have it is a conclusion. When tested relevant information appears within the perceptual span, attention guide is enhanced. So which indicates that information appeared within the perceptual span aids searcher to develop more useful searching patterns. The eye movement checks shows the correspondence between the tested relevant intelligent tangent to the tested relevant information within the perceptual span. It is the strong gaze, circuit gaze path could affect with useful perceptual span. Then the guide effect can be extracted to persist even if the subsequent test change. So more detail can find this paper on published on displays. So it's all my topic. Thank you, everyone. Thank you, UCLIC. Thank you, Professor Duncan. So is there any questions?
Amazing, thank you. Yeah, really short, nice, detailed talk. Thank you. Questions from the audience? Any questions, comments, clarifications? I know it's been a long day for many of us. Go ahead, Martin. Who has the microphone back to you?
Thank you very much for this wonderful talk. Just out of curiosity, you focus mostly right now on 2D displays, right?
Yes.
So I'm struggling right now. It's like when working with 3D data and 3D saccades, for example, and you worked a lot about that. How would you transfer your work from the 2D space into the 3D environments, like when you have holographic environments and stuff like that? It's like, how would the gaze behavior change in the third dimension, basically, when we have the like depth? It's like more free, or it's like more informations around us.
Yeah. Yes. Maybe I can. Yeah. Is here. Yeah. The experimental is increase create screen, and it's needed to searching the tangent, and it's within the within is by I'm sorry. So we can record the reaction time, and also it's yeah, maybe it's could here. It's a second experiment. So the data could compare the experiment 1 and 2. It's the same searching tangent, the same test. So we can compare the reaction time and gaze duration, gaze count. It's needed to exercise and then to have this experiment.
Okay.
It's okay. Yeah.
Yeah. Thank you very much.
Thank you. Yeah.
Yeah, here.
Yeah.
Are there some difference based on the gender, maybe different age, when you do the experiment to compare the difference and the relation with each other? Are there some difference for this?
Sorry, could you please?
Yeah.
Yeah.
It means when you do experiment, do you do some research to check if the gender make a difference, and make gender age or something? Maybe the cognitive different group cognitive load when they do the search information, maybe researcher and children, they have different. Yeah,
I know.
How do you think about it?
Yeah, it's different in different participate. So enrolled it's 48 participate, all the graduate student or student in based engineering academic.
Okay.
So it's same group. The background is the same. Yeah. Yes. So
Okay.
if maybe it's different.
If you do, I think, how do you think?
It's maybe for children or for others. Yeah, maybe it's different. Yeah, it's need to have more experiment.
Okay.
Yes.
Okay, thank you.
It's very good question. Thank you.
Thank you for your talk. I wanted to ask about the target that's been observed.
Yes.
Was it always static in the studies that you were doing, or was it moving? I was just curious about whether there's any, I mean, could you describe a little bit more in detail the setup? Be curious. Thank you.
Yes. It's set the maybe it is the navigation interface, and it's the participant need to find maybe it's the tangent is to find, but can over there, and then it's a Chinese. I'm sorry. It's the information 1, information 2. Maybe it's the first is information 1, and then to find the it's restaurant and the oil station is to find the all of the same searching test. All of the same searching test of 48 participate. So we can got the data based on the same cadence, the same researching test.
Thank
Yeah.
you. And then physically, was the face and the object always in the same place? as
Yes.
well, or, oh, I see.
Yes,
Okay. So
the
there was
face,
no
yeah,
movement such as using your hand to
yes, it's
change the position.
you can
of the
see
object.
this. It's 500 of 550 millimeter. It's you can't find another because it need to record the it must 70 it must be 70%. But if her head right left, so it can't recording the eye tracking. So we have exercised the participant need only see the screen and have to do the search. Yes.
One more question,
Okay.
if I may. Do you the technology today
Yes.
allows us to study this with the static setup in the future? Is it interesting to also look at a moving object?
Yeah, I know it's
If-
could.
But is it not? It's not possible technology-wise at the moment.
yeah.
Is it?
Yes, I know.
too
So in the in the navigation traffic and so it's need a class.
Yeah.
Yes, class is okay. So it can, yes, it can easy to find another and to recognize the to record the eye tracking. Yes.
I guess that it would be very fuzzy data. It would be much harder
Yes.
to
Yes, we need, yes.
get the-
It's because we want to find
Clarity.
its perceptual span. So it's fixes the yeah. So we can guide it the future interface and to modify the the experiment material and provide another. So it's needed to continue to study. Yes. Thank you.
Thank you very much.
Thank you. Thank you very much.